All right, and that didn't help. Where did my PowerPoint go? Ah, okay, close. Yes, I know the computer crashed. We were right about, no we weren't. We were right about here. Okay, we got through that. Since we want this to be a linear circuit, the first thing we assume is it's in saturation mode. We can assume a couple of things about the circuit. If it's in saturation, this current equation is true. We're going to ignore the body effect. We're going to ignore the channel length modulation. This is the way I usually write it is just Kn over 2 VOV squared. That's the short version. But Kn is just Kn prime W over L. And VOV is VGS minus VT. In that form right there, I can solve for V over voltage, and I can get V over voltage from ID. So if I know the size of the transistor and I know ID, I've got V over voltage, I've got VGS. If I know VGS, the size of the transistor, I know ID. If I know ID and VGS, I can pick the size of my transistor. This is where we left off, the dreaded differential pair. It's really not that bad, especially at this point. So I'm given some information here. I've got VDD is 1.8 volts, so I'm going to write that down. VTN, Kn prime, M1 and M2 are matched. Back when I was an undergraduate, people would try to build this differential pair using transistors out of the cabinet. It's impossible. You have to have transistors that were made on the same line, same day, right next to each other. You can buy pairs of transistors in a package, and those work, but you can't just pull 2 transistors out of the bin and expect this circuit to work.
Why not?
Because they're not matched. Their W over L's are different, so their channel resistances are different. And in order to balance the circuit, both halves of the circuit need to be exactly the same. Even this RD1 and RD2, if I'm using really precision like 0.01% resistors, there'd usually be a grad student somewhere measuring resistors to find the 2 that were the closest match, just to make this circuit work. It's not a great circuit for building on the board, but if you're inside an integrated circuit, you're going to put transistors where RD1 and RD2 are. They'll be matched, and the M1 and M2 will be matched because they're built on the same line on the same day. And this circuit works remarkably. And this is really the heart of an op-amp right here. And we'll be talking about this quite a bit. So the W over L's for the transistors, 50 lambda over 5 lambda, that looks like 10 to me. We want VD1 and VD2 to be 1.5 volts. And there was something else in here. Oh, ID3. We want this to be 50 microamps. Okay. We know, and I didn't even calculate this. So I'll just go through, I'll get the rest of it. We know ID for this transistor. Vref, since the source is grounded, will equal VGS. We could easily find VGS3. I don't think I actually calculated that because I was looking for the differential part of this. I actually had time to look at this morning. My schedule's not so crazy. There we go. Okay, now the thing that you kind of need to get here is I've got 50 microamps. This M3 transistor is acting as a current source. I can feed VREF into this differential pair, feed the same VREF to some other differential pairs, and they'll all have the same current if I use the same size transistor. Now, what's going to happen here if these two halves of the circuit are perfectly matched? The transistors are identical. They have the same W over L, the same on resistance. The resistors are perfectly matched. They have the same resistance in there. And VD1 equals VD2 exactly. Then I've got 50 microamps being split between two identical circuits. What's the ID of M1 going to be? 25, yeah. It's split exactly in two. Okay, we got that far. Now we've got ID. We can get a value for this resistor right here because I've got the voltage on both sides of it. The voltage drop across that resistor is 1.8 minus 1.5. And its current is 25 microamps. So the resistance, RD1 and RD1, is going to be, when I plug all those numbers in, this is going to come out to be 12 ohms. Okay. RD2, what?
Sorry, we know the current rate has to be 25 microamps because it's matched.
Right.
And current Dr. says that we split even.
Yes. So it's just like, it would be like a current divider where I have a current source feeding into two equivalent resistances. The currents are going to be the same. Because they're matched, I want RD1 to equal RD2 down to a level of precision you can't imagine. That's hard to do. It's easy to do in an integrated circuit. Okay, so we've got that far. We don't know what VS is yet, but we know the current of M1, and we can calculate its V over voltage because we know the current. So VOV, and it's really important at this point to get in the habit of saying, this is VOV of transistor 1. Use those subscripts. It will keep you from going batty when you're doing these calculations. VOV1 is going to equal the square root of 2ID1. Believe me, I know I went through this the first time I taught this class. Times its Kn, and that's Kn, not Kn prime, W over L, 2ID, wait, now oh, yeah, Kn W over L. And we plug in the numbers that we've got here, the 25 microamps, the Kn is, it's an N type, so 200 times W over L is 10. And we get VOV1 is got to be 0.158 volts. And VOV is VGS minus VT, so VGS must equal VOV plus VT. And that's 0.4, so this is 0.558 volts. Okay, this was a good trick to know. I've got, this is where VGS is. It's the voltage between the gate and the source. 0.558 volts. No. So the source voltage, the people in the room know what's going on, you guys don't. The source voltage will be VDD over 2. VDD was 1.8, so it'll be 0.9 minus 0.558. 0.342 volts. I stopped writing for a reason. And we can get BGS3 using that current equation. Key thing that's new here is the current splits equally between the two devices because they are perfectly matched. That's as much as we're going to do on the differential pair today. I hate the look on my face. I'll be back in a minute. I'm sorry. Slide. Okay.